try this. What information do protons give us? They identify the element. Okay, so that's really our symbol. What do the neutrons tell us? Okay, it is the mass of our element, known as what? We'll come back. That's atomic mass. How can I ask this and get the answer I want? Okay, fine. I'm just going to tell you. Isotope defines our isotope. Remember, we change the number of neutrons. We don't change the element, but we are changing the mass, so we get a different isotope. Okay. And then the last one, our electrons define charge. Okay. So the reason I'm writing this out is because probably you're asking this question and you don't know where all that information is written around our symbol. Okay, so the very first thing, we need to come up with a symbol. What's going to determine the symbol? Number of protons. Okay, so we would use the periodic table and find where it says 25 protons. Does it ever explicitly state the number of protons on the periodic table? It gives you a number, but it doesn't give you the context of what that number specifically means. So I know what you're doing. You're doing an interpretation on top of that, Hunter, but that interpretation may not be obvious. The number of protons is specified as the atomic number. So when we look at the periodic table, the atomic number we know is given where? Top right. How do we know it's on the top right? Because that's what the key says. Use the information you have. The key on it tells you. Okay? So that's our atomic number. So if I want 25 protons, I need to find the element with 25, which is manganese. We just run with Mn, which should immediately help us out because we can then get rid of the first two answers. Okay? So worst case, you're now down to a 33% chance of getting it right as opposed to 20. Not too bad. Okay. Where's the rest of that information specified? So now we run into an issue on where the atomic number is given, okay, versus the mass versus the charge. Okay, so we've done it the simple pass. So now the more complex pass. Charge. Is the charge ever given to you? Yes, it is always given to you. Where is it given to you? In the top right corner. Are we changing the charge? Are we changing the number of electrons? Why were you given the electrons? To confuse you. That is the only reason the electrons are specified. Because someone's going to go through and say, well, what happens if I add 25 with 25? I get 50, which doesn't add up on there, but that's theoretically what they're doing. They're providing another numerical value that you could then add or subtract to potentially get one of the answers written there. Okay? It's testing you, do you understand something about chemistry? Charge is always specified in the upper right-hand corner. If there is no charge in any of our answers, the electrons will not change. They must equal the number of protons, which means electrons are irrelevant to our question. I don't care to even look at that. Okay. So, the next part is figuring out the atomic number. Okay, the periodic table has the atomic number where? Atomic number. Top right. So it's on the top. So maybe we put the atomic number on the top in our formula. Okay, does that answer show up? Yes. Putting a 25 there. Oh, interesting. It doesn't go there then. Which means, where should the 25 go? On the bottom. Where is it supposed to be written? On the bottom. Did you need to know that? Well, yes. No. To answer this question, it was completely irrelevant. Because at no point was 25 written in the upper left-hand corner. use a process of elimination in your thought process when you go through and deal with these. Okay? Heidi, you had an interesting point. Why are we specifying 25 in the lower left-hand corner when the periodic table has it in the upper right-hand corner? I'll step back a little bit from what Simon was suggesting in the corner, because chemistry. Right? And probably a little bit worse than that, it's not the chemistry's fault, it's the chemist's fault. It's the person projecting their thoughts onto it. Okay? Why? I don't know why they chose this format and decided to switch it there. Okay? But that's how it was written. Okay? So what does that help us with? If the 25 must get written somewhere in there, it can get written in the lower left, which then means D is wrong. Okay? Now what are we looking at? We're either writing a 55 at the top or a 30. What does the 30 correspond to? The number of neutrons. And since neutrons contribute mass, maybe we're adding that extra information in. We're specifying the mass of the isotope, or the mass of that element. So we could go through to write 30. But we have to be careful. Do protons carry mass? Yes. So when we specify that the neutrons determine the mass, it's on top of the protons that are contributing mass already. Which then means the total mass for that isotope is 55, the 25 plus the 30. Then we get 55, and our answer becomes C. Kind of makes sense? So, two approaches. The one approach we just walked through. Process through the information you have. Okay? Pull something that you know from the course and try and eliminate answers to cut your losses. Okay? The second approach, no one's going to like this one. You memorize that that's the notation. That's where it goes. Okay? Those are your two approaches. What's that? None? Okay. The long process of thinking through each and every single question would probably take more time than you have on the exam. So ideally, you spent some time memorizing some content that you get some of those answers correct. The ones that are harder, that you aren't as familiar with, you can work your way through, okay, and try and eliminate answers. Yes?
Is the actual test shorter than the review?
The actual test is shorter than the review, which is probably a good thing, and now you're all happy, but not by that much, only 3 questions. So, the actual, it is, but the actual exam is 65 questions.
Is it all multiple choice?
It is all multiple choice. Yep.
Is there some English questions?
No. So this is a standardized test within the department, allowing us to kind of see how different sections of chemistry are doing. So in theory, everybody coming through Chem 130 takes this, and we can say you learned the material because of this test.
Which is all the more reason for you to like represent the learning community right now and like do awesome on this exam.
That is what we are hoping to see. So, Adrian, did that answer your question?
Yeah.
Okay. Let's pause. We had the symbol. Whoops. Yeah, I had that right. Whoops. No, I didn't. We had the mass number, and then we had the atomic number. Okay. We read question 17. What is the term for the value which indicates the total number of protons and neutrons? Okay. In an atom of a given element. Okay, well, that's the number of protons and neutrons, and it contributes to the mass, right? I thought the word mass was up there. So which of our answers include mass?
C and D.
C and D. Isn't that pleasant? So ideally, you'd be able to narrow it down to one of those two answers. Okay? And this is where we run into a definition thing. And if you go back and watch the lecture when we first talk about this, I spent an extra second talking about this for this very question because I find this irritating. What is the difference between the mass number and the atomic mass?
The atomic mass is like the average mass of all the isotopes.
Atomic mass is the average mass of all isotopes for that element. That is what's on the periodic table in the lower part of it. That is our atomic weight or our atomic mass. The mass number is defined as the number of protons and neutrons. So when we look at this question, our answer is the mass number, not the atomic mass, which is irritating because they're tripping you up on that word mass. We have to be very careful sometimes with our definitions and what they mean and how we apply them. Okay? But that becomes relevant with question 19, because in 19, what are you being asked to do? The mass number is just protons and neutrons. So that should just be an addition question, which is fine. We could ask that. But what are you being asked for? The atomic mass. And if we're being asked for the atomic mass, is that just going to be addition and subtraction? Or no, we're being asked to calculate an average. So we have to determine the average and use that information to help us predict what's going on. Okay? So we could go through and say that our atomic mass is just our average. If we take an average of the two masses, what's the mass of particle 1? Thank you for volunteering a number on that. I do appreciate that, because it was kind of an ambiguous question. Plus the mass of particle 2, 0.916. So we add up our terms, and then we divide by 2. We'd get a number, and that number shows up as one of our answer choices. That answer also happens to be wrong. Okay? When we're going through and looking at an average, okay, what we're used to dealing with is just a standard average. We add things up and we divide. Okay? But that requires that we know each and every single one of the things that we add up. Okay? So we could average 1,000 numbers. Okay? But when we're determining the atomic mass, we aren't averaging 1,000 numbers. We're averaging probably on the order of 10 to the minimally 23. Probably looking at several orders of magnitude higher than that. Okay. If you just entered a single number, any digit, just do 1 and then return 1, return in Excel, just to enter in all the values so that you could then have Excel calculate the average, you would die before you entered in all those ones. Okay. So looking at the individual values doesn't work for us. We can't just take a normal average. What we have to do is take a weighted average. That's where we're looking at the percentages. Okay. So it's the percent of atom 1, which let's go ahead and call it percent of atom 79, times the mass of atom 79, which in this case is 78.918, plus percent of atom 81 times its mass, 80.916. Okay? So I need to look for the percent of atom 79. Where's the percent of atom 79? What is it? Okay, it's given to us. It's that 50.69. So I could write 50.69. Okay. Is 50.69 the same thing as 50.69%? No. I don't know why I could move the mouse, but that's cool. What does the percent mean? Per 100. That's what percent by definition means. So if I want to do that, I need to put in per 100. Okay. As Hunter was suggesting, the other option, say, well, it's so much easier to do that. You're doing the exact same thing. Nothing's different. You're doing the exact same conversion. You're shifting the decimal by 2 places because you're dividing by 100. Okay? We can then multiply by our mass, 78.918, plus the percent of atom 81. Where does it say 49.31? We're only given two isotopes, so what we're assuming is the percent of isotope 79 plus the percent of isotope 81 must equal 100%. If I know 79 was the 50.69, I can then solve for that unknown term, and I can plug that value in. What'd you say it was, Hunter?
49.31.
Again, it's a percent, so I'd have to put it over 100 times our value here, 80.916. I can now punch it into the calculator and I get my official answer. Make sense? Is there a shorter way? Okay. It's an average, so our answer should show up where? What should its approximate value be? Or rather, what should its approximate value not be? What's that? Why are you saying 119 and 120? The average of two values shows up where? In between those two values. 78.9 is as low as we can go. 80.916 is as high as we can go, which means answer choice A and answer choice D are wrong because both of them are above. Do we have one that's below? Yeah, we do. 79.9. Okay. We're at 50% odds of getting this question right, and we did no math. That's pretty good odds. Okay. How to propagate closer? That one becomes a little bit more dangerous, and what you end up trying to do is manipulate your percentages and say roughly what it would come out to be, which means you're ultimately doing the calculation in your head. So just write out the calculation. Don't do it in your head, put it on the calculator, you're done. Hi? Yes? Oops, sorry. I can't do math. No, yeah. I saw the 0.9 and I assumed it was lower here. That's 78.9. You're right. 78.9. Anything lower than 78.9 is wrong. 79.9 is clearly larger than 78. Okay. 80 is clearly larger. 79.93 also clearly larger. So we don't get all the way down to 50%, but we're at a 33% chance. Thank you for pointing that out. Okay. According to Sebastian, if you punched in all the calculator, the answer you get is B, with 79.90. Okay? So, Adrian, that solved your question. Okay? Other questions? Yes, Emily. This is as close as you get to a history question. Following the X-ray emission studies of Harry Moseley in 1913, the order of the elements in the periodic table was based on which of the following? Okay. So all you should really read is order of the elements in the periodic table. As we move from hydrogen to helium, what happened? Atomic number increases and atomic mass increases. If we go through and check, we'll notice the atomic number and the atomic mass both increase for most elements on the periodic table. Okay? And that's where this question could become a bit tedious because you'd have to go all the way through until you found the place where they did not match. Nope, I have problems apparently with larger and smaller. 52 and 53? Yeah, there we go. As we go from 52 to 53, that number gets bigger. What happened to the mass? The mass got smaller. Is the periodic table organized according to mass? No. It's organized according to the atomic number. Now we can go in and find that answer. Okay. Did you just say what is the periodic table? Is that what I heard?
No,
So why does it mention Harry Moseley?
Confuse us.
kind of to confuse you. Is that a true fact? Is that why the periodic table is organized the way it is? Yes. Yes, it is. Okay. So would anybody remember that? No. Okay. So it's really just a question of, do you know how the periodic table is organized?
So it's atomic number.
Yes.
Okay.
Which?
It's B.
B. Thank you. Does that work for you? So in something like this, you have the periodic table. Yes, it was tedious to try and go through and find where the mass versus the atomic number didn't match up, but you could go through and do that. Okay, so it's again one of those things. You have the tools, take advantage of those tools. And 1913, time-wise, is kind of late as far as chemistry goes, so it's probably that. So we've got the directions. We'll do the whole name thing that we've been doing again. Put away all your materials, all that kind of fun stuff. Don't cheat. Good luck. Have fun. That kind of thing.
First one done, get the name.
The next page will have your periodic table of the elements. Okay? So let's think back to the exams that you've taken this semester. At the end of the exam, how many of you forgot your name? Like you walk down and you're like, I have no idea who I am anymore. You walk in and you're like, I must be Mike, because I did so well on that. Okay. Very, very rare for anybody to take an exam and forget who they are. Okay. But what are the odds that you're going to forget the trend in the atomic radius?
A lot higher.
A lot higher. So maybe what you should do after you've gotten the name of the people around you is flip to the periodic table and put down some useful information. Not just the periodic table, but there's half a sheet underneath that periodic table where you could write useful information down that you no longer have to keep stored in your brain, like atomic radius. Okay? Because it's a multiple choice exam, you won't get some jerk instructor asking you to explain the atomic radius transition. You'll only get what is the radius. Okay? So if we look at our radius, what happens?
Get smaller as you go towards helium.
Okay. As we go towards helium, it gets smaller. And since you have that jerk instructor now, why? Chemistry. Okay. We end up putting in electrons at the exact same energy level. As we move across a row, we're in the same energy level. So the electrons are at the exact same distance away from the nucleus at first blush. At second blush, we realize, what have we done to the nucleus? We've made it more positive by adding a proton, which means if I put a negative charge or one magnet of equal strength near another magnet, but I increase the strength of that other magnet, what happens? It gets closer. You could probably tie something back, but don't. So when we're looking at atomic radius, what happens, and how you decide to draw your arrows is up to you. I would probably draw them like this, and I would write atomic radius. Okay? Meaning, and I might also add big. Okay? Because as I go to the left, that is left, right?
Yes.
Left, correct. And down, it gets bigger. I now have that information, so when this question pops up, I'm not thinking about, okay, what was the trend? It's, oh, I wrote it down on the front of the exam when I was fresh-minded. Not 30 questions in when I'm lost my consciousness. Okay. What else might be useful to include on this? Charges. Okay. What charges are you aware of? +1, +2. The +3 is a little bit weird because you're only responsible for aluminum, but it works there. Carbon is a question mark, then it goes -3, -2, -1, and noble gas, so no charge. And then probably the more important ones would be zinc and cadmium as +2, and then silver as a +1. I now have charge information specified on this. Was purple a bad color?
No.
Purple works? Okay.
It's always +1.
Silver's a +1. Right? You now have all of those things that you may have been spending your time memorizing because you didn't think to write it down. It's amazing. Write stuff down, and you don't have to think about it. It's kind of cool. English. Yes. All right, what else might we include? I think I heard it there. Our electronegativity, which is our most electronegative element. Fluorine, so our electronegativity increases left to right and bottom to top. Big. I personally don't like writing out electronegativity, and so happen to look up the accepted symbol for it, which is chi. That is up to you if you want to remember it that way or if you want to write down electronegativity. But again, electronegativity is too big of a word for me. Partnered in an English class. I shouldn't be saying these things out loud. Okay. I now have that information specified. It's easier for me to then recall. So that now when we get to Hunter's question, I got to move stuff now, which was which of the following has the smallest atomic radius. I don't have to think through trends. I've already drawn it on the periodic table, and I know the smallest atomic radius was in the upper right-hand corner. Which of those is in the upper right-hand corner? Fluorine, I'm done. There's zero comparing things, I'm there. Make sense? Okay, Tanner, I think you had another question?
Yes.
So apply like dissolves like rule immediately. As soon as I see this, I would say apply the like forces dissolves like forces. This gets written on the exam. This is now an interpretation. I'm not comparing like dissolves like. I'm comparing forces to each other. And now if I skip this question and come back, I'm not restarting from the ground up. I have some information to work from. Okay? Which of the following liquids is miscible with water? What does miscible mean? Okay. We could say mix. Could also say dissolves. Could also say soluble. Okay. Whichever of those trigger first for you is what you should specify with water, and then it lists a whole bunch of compounds. Okay. It's going to be easy to get lost in all of those compounds, so let's go back to what we said. Like forces dissolve like forces. How many times does forces show up? Twice. But I can only choose one answer. I can only choose one answer, but I need two things. What's going on? Water is also specified. So what I should also be tagging here is identifying water and saying water, hopefully we know the formula. Thank you. I've been practicing that at home. Water, what are the forces that I would expect out of water? Okay, and we run into a couple things here. I heard base. Acid and bases are reactivity, not forces. How do we determine forces? Where do the forces come from? The charges which come from the type of bond. Okay. What type of bond do we have in water? Okay, I heard a lot of answers, none of which I liked. Covalent is wrong. Hydrogen bond is also wrong because I asked for the bond. Hydrogen bonding is not a bond. It is a force. And yes, that is our correct force, but we aren't there yet. Answer the question. Dipole-dipole is also a force. It is polar covalent. Sorry, Andrew. A polar covalent bond results in what type of force? A dipole-dipole force. Okay, which again, on a test, I would start to get lazy and probably write D-D. Okay. If I have a dipole-dipole force, what should I look for? Potentially another dipole-dipole force for the answer. But there's something else that you should identify first. If we have hydrogen bonding, do I have a hydrogen bound to oxygen, nitrogen, or fluorine? Yes, which means hydrogen bonding. So if we go back to our initial statement, like hydrogen bonding dissolves like hydrogen bonding. I'd better see hydrogen bonding in my answer if it's going to mix. Okay? To identify hydrogen bonding as an answer, what did I need to see? A dipole-dipole force. I needed to see a polar covalent bond. And in particular, which polar covalent bond did I need to see? Hydrogen bound to oxygen, nitrogen, or fluorine. All of them have hydrogen. Only one has hydrogen bound to oxygen. So your answer is D. Make sense? Does that work for you, Tanner?
Yeah.
Okay. And I think 68 adds another layer on top of that. But we're good with that?
Yes.
Okay. You said 68, right? Okay. Almost identical. Apply the like dissolves like rule. If this showed up on the exam, I'd already written that information, so I'd probably pull out question 66 so I could look at that information at the same time, because I've already done the work. I'm just applying that work a second time. Okay. What things changed about this one, though? Okay. It's not bromine. It's not water anymore. It's bromine. What type of bond is in bromine? Officially are non-polar covalent, but yes, I tend to refer to them only as covalent. Again, that whole laziness thing. If it's non-polar covalent, that gets us what force? Our London dispersion force. Okay. And so I might immediately jump in and say, okay, I need to find my London dispersion force. Oh, answer A, carbon and hydrogen. Those are non-polar covalent bonds. That gives me London dispersion choice. My answer is A. Why are you shaking your head no? What is B? The exact same thing. Oops, maybe I misread something. And I heard somebody shout it out. What did I misread? This says not. A and B will mix. That is my like dissolves like. I want not, which means I want something that is not like London dispersion. What is most not like London dispersion? Officially electrostatic forces, so we could look for an ionic bond. There is none, so we move to the next one, which is hydrogen bonding. Hydrogen bonding as our solvent would be D with water. Just to be mildly irritating, let's get rid of D as an answer. What's our next answer? Probably going to be carbon tetrachloride. For what reason? Polar covalent bonds. Those polar covalent bonds could theoretically produce dipole-dipole forces. For anybody listening at home and is screaming internally, yes, there's a structural effect. You don't need to worry about the structural effect for this exam, so don't worry about what I just said. Your answer is D, water.
149.
Tanner, does that answer your questions?
Yeah, those are just
What's that?
yeah, that answered my question. I'll do it.
Just said
All of these kind of questions, when you're seeing structures drawn out, will require more time and more thought. There isn't a calculation. You can't punch something into the calculator and have it spit out your answer. You will actually have to think, okay? Which, as you might guess, are awesome questions from an instructor point of view, and they're really crappy questions from a student point of view, because you now actually have to work for them. Okay?
Can we do 45?
So, next one. This part of it. what you should be coming up with when you go through and do any kind of practice work is coming up with a process. Excuse me. The sandwich tasted good both times. You need a process to go through and solve. Solving any individual question is meaningless unless there has some kind of value behind it, a point value. So just coming up with the answer to this question doesn't help you, because you won't see this question, you'll see a variation on it. So what you need to do is come up with the process. How did you approach this? Okay. Which is what we did with the previous ones. We are adding information to our question so that we don't have to do that interpretation. So the first thing that I would do, identify what I'm trying to do. I want the percentage. And in particular, I want the percentage of platinum. Okay. So I want platinum in or per what? In the compound. What was the compound?
How do you say
Xenon. Oh, I guess that wasn't really fair. We haven't talked about how to name that compound. Does anybody know how to name it? It's xenon platinum hexafluoride. I'm actually not positive on that. I think that's right. But I figured if you didn't know, I could make up anything I wanted.
But you're using principles of nomenclature to try and build it, right?
I am using the principles of nomenclature to slowly build that formula out. It's probably technically wrong. Yeah, whatever. Okay, so yeah, I've been proven wrong. It's not xenon platinum hexafluoride. Okay, so I need the amount of platinum and I need the amount of the whole compound. Okay, so if you were asked to find your percent in this class, what would you do? Hopefully you'd think a little bit more than just looking at Canvas, but you'd look at your total points that you've accumulated throughout the semester, which you could get from Canvas, and compare that to the total possible. So we're looking at the parts of platinum in a xenon hexafluoride platinate? Hexafluoroplatinate, there we go. Okay, compound. So what do we compare? What is our numerical value that we should be using to compare here? Mass. Okay. Is it obvious within the question that that's what we should be doing? I would argue not. It should be much clearer in the question. You're running from context of how we go through and solve these kind of things. Okay? And I believe I even used that term correct. Okay? The context for solving our percentages are almost always mass percent. Okay? Sometimes they can be volume percentages. Okay? Are we given any information about the volume? No. Are we giving any information about the mass?
Yeah, no, well, we can look at it on the periodic table.
The periodic table gives us what? The atomic mass. So we do have information about the mass. We know platinum happens to be we know xenon happens to be. We know platinum happens to be. We know fluorine happens to be, as I run out of space, 6 times of it.
6 times
Was it?
19 is 114.
19. And we can now go through and calculate. So what we're trying to do is identify our individual steps and then slowly process our way through it by finding the information that is admittedly buried somewhere else. Okay? If you look at a question, you're like, oh, I don't think there's enough information here. Look at the periodic table. Okay? That was part of the class, was understanding the information there. We've got a lot of information stashed there. When we go through to calculate that, we then end up with our correct answer. One common mistake, students tend to leave the platinum out of the bottom. Okay? So what you would be solving for is platinum, the amount of platinum in xenon hexafluoride. Is there any platinum in xenon hexafluoride? No. You have to include the platinum. Otherwise, it's zero. Okay? Make sense?
So you don't have to like divide by 100 to get the percent?
So officially, to get the percent, you would have to then multiply by 100, because what you're going to get here is a fraction or a decimal value, and then you multiply by 100. Okay. Simon, you talked through a different, or let's try this first. What's the answer? Anybody actually do it in the calculator?
44.
Everybody got 44? Okay. Simon didn't use a calculator, allegedly. So elaborate. How did you get the answer without using a calculator?
6 times 19 is 140. So I said that E couldn't be right because it has to be roughly around 33%.
Pause. Why'd you say 33%? We have roughly, it's not even roughly 100, but if we just look at the first part, 100 divided by 100 plus 100 plus 100, that's 33%. So we can estimate that 33 ballpark is close, so 4 absolutely makes no sense.
And then B, because it's not right because it's too high. It can't be over 50%.
Okay, because yeah, the 100 is smaller than 300, so that can't be right.
And then I said E was wrong too because I said E and A were wrong because it wasn't around 33%.
A's, well, you're telling me A is further from 33% than 44? So we can still eliminate answers there. We can start to look at what approximations or assumptions we made in solving that to help us narrow that down without using a calculator. Okay. So again, estimation is your friend. It can help you through it. You have a calculator. I would argue just use it if you got it. If you don't got it, then that's fine. But
So with me looking at this, that I guess along the lines of what Simon's saying is the percentages aren't close enough for you to have to worry about the really deep math. You can round 195 to 200, 130, 1.3 to 130 because you just need to get in the ballpark. So you don't necessarily have to do all the deep math. And so if you can do basically 200 over, what is it, like?
And I would admit I would probably do that.
It's like 440.
I would say ballpark 50.
And then it's just a little bit more than that because the denominator is just a little bit more.
But it also gives it some room, because, like, I'm sorry, like, from what he was saying, you're at least 33%. All the other percentages are below it, other than 44.
A lot of that comes down to how you did your rounding. Yeah, on the at least 33%. Okay. Does that make sense? Are you okay with that one?
Yes.
Okay. First we got to do Sebastian, because Sebastian suggested something. What did you say it was?
23.
Which of the following is the electron configuration for an atom of nickel? So electron configuration, you might already kind of pause at and be like, oh, really? And then you probably see that string of S's and numbers and P's and D's and all of that. They're probably also going with. Okay. This one turns out to not be quite as bad as it may sound. First interpretation. Okay. To get this information for my electron configuration, it's the number of electrons. Where are the number of electrons stashed? Where do we have that information stashed? Kind of our atomic number, yes. But what am I looking at? Periodic table. The periodic table gives me information about where the electrons are located. So again, use the periodic table. But when we use the periodic table, does it tell me what nickel is?
Yeah, it does.
No. Nowhere on the periodic table does it say NiCkel. Okay. you have a layer of interpretation in it. That layer of interpretation is that what the periodic table tells you is Ni. You need to know the element symbols. So we find nickel, and where's nickel located? Okay, we're in the 4th row. I don't think I want to write that. I'm not going to write that. Yeah, give me some other information about it. It's in the transition elements. I like that. Transition elements refer to what orbitals? The d orbitals. So the last electron should go into a d orbital. Okay, how many electrons should go in for nickel? I know where you're going with the 28. Why 8?
Because if you count from left to right in the d orbital section, 8.
All I'm referencing now are the d orbitals. That's it. It's in the 8th column of the d block, which means that needs to be d8. Come on. Okay. Which energy level is it? Okay. This one gets tricky because our energy level is whichever row it is. It's in the 4th row, but our d orbitals are offset by 1. So it's officially a 3d. If you didn't remember that, let's go through and look at our answers. So, in answer choice A, do you see 3d anywhere? No. Do we see d anywhere for that matter? No. So, wrong. B. Yeah, there it is. C. Oh, unfortunately, we do have a D8 there, so that could get a bit challenging. We might actually have to do that interpretation. D. No d orbitals. Not even enough number of electrons. E. Okay, so we're now between B and C and trying to decide what happens. If we compare those out, they're identical except for that number in front of the d orbitals. So we have to know a little bit more information. The d orbitals are offset by 1, which means we are filling the 3d, not the 4d. Okay, you were shaking your head no. Did you have something else to add? No. Okay. I was hoping you had a different trick. Okay. So we have to know it's 1 less. So the first row of the d orbitals is in the 3rd energy level. It's the 3d. Our answer choice is B.
So as soon as we knew it was a transition, we knew we could kill 3 of the answers?
Yep.
Just all right off the bat.
So did I have to provide the entire electron configuration? No. Why did I start with the Ds? Well, that's what makes it the most different from all the others. That's the outermost electrons. Okay? That's the easiest place to work. If I had to, I would continue to fill in everything else. I don't have to here, so I'm not going to worry about it. Okay? Your other option? Draw it all out. I'm not going to do that for you. That's not an option for me. Okay. Does that work, Sebastian? Okay. What was yours? 54. I usually like sharing my approaches on exams. The instant I see this question, any ideas what I do? Pretty close. I skip it. I skip this question altogether. Any ideas why? This again, this is not
to
good.
read. To read.
It's a lot to read.
It takes time to read that.
Okay. I'm going to assume that there's too much content for me to interpret. I'm going to move on to a question where I don't have to interpret as much. The interpreting process for me personally takes time, and it's going to break my brain. Okay? So I will answer every other question that doesn't require me to interpret, because then my brain is more fresh for those questions. I increase the odds of getting those questions right. I can come back when my brain's already broken, but I was already going to get it wrong anyway, so who cares? Okay? That's the thought process that at least I work with. Okay? Acceptable losses. But because you asked this one, didn't you?
Yes.
Yeah. But because Megan is now forcing me to answer it, I have to go through and actually do it. Okay? So, potassium metal and fluorine gas react to form potassium fluoride. Which of the following statements is true? Oof. Okay. At least it says true. Okay. It could say false. That's even more fun. Okay. The potassium atoms lose electrons and fluorine atoms gain electrons. This sounds an awful lot like redox, which was everybody's favorite chapter. That was the oxidation states.
Please tell me it's not in it.
Yay. Potassium atom is smaller in radius than the potassium ion. Oh God, that's hard because I got all those trends. Oh wait, I wrote that down on the front of my exam. I could go back and start to use the front of the exam to help me out. Okay, and I would find that answer or choice B is careful. Potassium ion, atom is larger or smaller in radius than the potassium ion. Oh crap. What did I write on the front of the exam? The atom radii, not the ion radii. What happens when we become an ion? It gains or loses. What does potassium do when it becomes an ion?
No, loses.
We had it written on the front of the exam. It says it's +1. So when it becomes an ion, it lost an electron. What does our radius, or what determines our radius? The number of electrons. If I get rid of electrons, what should happen to the radius? It should get smaller. The ion radius for potassium is smaller than our atomic radius. So we have to be careful. So it's flipped, which means that answer is false. Answer choice C, the fluorine atom is larger in radius than the fluoride ion. Oh crap, you're making me do the same thing, except now what's trickier about it? Why is fluoride gaining an electron? Didn't potassium just lose one? Fluoride, when it becomes an ion, gains an electron. That's why we wrote that -1. Well, if it gains electrons, what should happen? It should get bigger. So our fluoride ion should be bigger than our fluorine atom. That's false. Okay. Nice thing about calling both of those false, what is E? Also false. So we're now down to 50-50. The potassium ion and the fluoride ion bond by sharing electrons. And well, I'm forming a bond, so that does sound like sharing electrons. And this is where this one becomes challenging, okay, because it's going back to strict definitions. So the best way that I would approach to writing this out is, or answering this, is writing out the chemical equation. We have potassium plus fluorine form what? Potassium fluoride. Okay. What type of bond do I have between potassium and fluoride? It's an ionic bond. And in an ionic bond, do we share electrons? No. Okay. That is part of the definition of an ionic bond. It technically does not share electrons. Okay. I admittedly answered D when I first read this question and saw that I was wrong, and wrote out this equation to see what was going on with it. The instant I had the equation, answer A becomes a lot more apparent. If we remember our redox. Potassium atoms lose electrons. What happens to the potassium to go from this potassium to this potassium? I'm starting with 0 charge, and I'm ending with a positive charge. How do I become positive? I lose the negatives. Oh, there's the loss of electrons. Okay, what happened to the fluorine atoms? Started 0 and it became negative. The only way we become negative is by increasing our negativity, okay, by adding electrons or gaining electrons. The equation answers the question almost outright. Okay. So you can even see in my method of skipping the, actually, in my method, I said I would skip it, come back to it later, because I was inevitably going to get it wrong. And what happened? As the instructor of the course, what did I do? I still got it wrong. Okay? We have to be very careful in how we approach some of the English language in the chemistry context. Get rid of the English, make it chemistry, your answers become more apparent.
But I like one of the best things you did there, which is you said you start out by playing to your strengths. Get
Yeah.
the questions you know that you know that you know, because it's all worth the same amount of points. Get those ones out of the way first.
Yeah. Your very first question is the easiest question. Is everybody going to have the easiest question? No. Everybody's easiest question is different. Find yours. Okay? And work through the exam that way. Okay? Other questions? Because that's good enough for you? Good. What? Was there another question? Oh, answer A. Question, sorry, 40? 20. I just realized I'm recording this whole scrolling thing. It's probably going to make someone sick if they watch it. It's kind of hilarious. So sorry if you've already vomited. Okay. Question 20. Which of the following energy level changes for an electron is most energetic? Okay. We saw a variation of this question on your practice exams, though I was proving that it was not the exact question, but it's a variation on it. Okay. We're talking about electrons jumping. Jumping from where? From orbitals. Okay. Are all of those, so that is point A to point B, but we're being more specific with orbitals. Are all of our orbitals at the same energy level? No. Where are our lowest energy orbitals? Closest. What do I call the ones that are closest? Keep going, because it didn't say S. How would I identify those orbitals? As 1, by their energy level. 1, 2, 3, 4, 5, 6. Okay. Our lowest energy level is 1. Man, no energy level 1. So we're starting with 2 as our lowest energy level. Okay. If I jump from 3 to 2, I'm jumping 1 level. Okay. I'm jumping from the second floor to the first floor. Or first floor to the ground floor. Do I survive that jump? Yeah, I'm pretty good. I can bounce. 4 to 2. Okay. My odds of surviving are starting to shrink. Okay. It's only 2 4s. Maybe I break a leg. Spider-Man. I don't know. There's an awning. Okay.
Well, if there was an awning, then that
3rd to 2nd. 4th to 2nd. Which of those am I least likely to survive? 6 to 2. Why? Let's see if I can pull it. I believe it is you two, actually, that can answer this question from your blog. Why am I losing the most energy 6 to 2? Why is that the biggest energy jump? Because at level 6, I have the highest potential energy. As I drop, I am now losing that potential energy, and I'm converting it into kinetic energy, my motion, as I move down each floor. I'm going from 6 to 2, I have 4 floors of energy that are now allowing me to move. Okay, and what happens when I hit the 2nd floor? That now transfer of energy is not a nice flying feeling. It's instantly being transferred into 0 energy.
Unless there's a big marshmallow.
That's going to result in probably death. Okay? That is our biggest jump. That's all it's asking. That's 40 feet.
Okay, yeah, that makes sense.
It would probably at least really, really hurt.
Like you break it.
There's actually another layer to this one.
Did you say 4
Okay.
floors? 2 would.
No way.
No, 2
You
would
could
take.
survive 2.
Oh my gosh.
We're not testing that, by the way. As we go higher in energy, what happens to the gap between the energy levels? It gets smaller. As I go from energy 1 to energy 2, I have a big energy gap. Going up to energy level 3, do I have the same gap? No, it's a slightly smaller gap. Energy level 4, slightly smaller, slightly smaller. Remember we're going out to our vacuum? Remember when we drew this? Work, pen. If that was 1, there's 2, there's 3, 4, 5, 6, 7. Okay. As we increase our levels, we're still going higher, though. Okay. That answer? The other thing to watch out for in this type of question, we don't have a not to worry about. What do we have to worry about? Most energetic, it could say least. If you go through and look at your exams from this semester, when there were most, least, nots, typically they were bolded or italicized to draw your attention to it. I'm being overly nice. Your final does not have that attention drawn to it. You have to read the question carefully. It helps to underline those big keywords. Yes, Jocelyn.
I was wondering if you could do number 46.
Yeah, we'll try and sneak out 46 really quickly. 46. All right, this is a good process one, but since we're out of time, how many moles potassium nitrate contain 8.68 times 10 to the 20th potassium nitrate formula units? Formula units is an irritating word. It means the exact same thing as molecules, except molecules is not an appropriate term because it's an ionic compound. We have to call it formula units. Okay? So you can treat it the same as molecules. So step 1, what do we want for an answer? Moles potassium nitrate. What did we start with? So I want molecules to disappear, and I want moles to appear of potassium nitrate. I wish I had a conversion factor that related molecules and moles. Avogadro's number, that's our 6.022. That 6.022 shows up in front of our molecules. 1 mole, we have our answer. All we have to worry about is what our answer is. If it comes down to sig figs, our sig figs are going to be dictated by the number we were given. How many sig figs in that number? 3, which means our answer needs to have 3 sig figs. If we take a look at answer choice D, we know the number 1 is significant, the 4s are significant. Are the 0s significant? For them to be significant, they must have a significant digit in front. None of them do. There's only 3 sig figs in that answer. I see you freaking out because you don't like sig fig rules. Okay? So you do need your sig fig rules. Typically when the questions are asking about sig figs, I apologize for continuing to talk, but I promise this is going to be the end of it, just because a lot of people seem to be freaking out about them. What you can expect for sig figs, here's back to that sick thing. Question 1 and 2. Those are the kind of level of detail that you can expect when you're being asked about sig figs. In question 1, how do we know we're being asked about sig figs? It says so. Okay. Question 2, how do we know we're being asked about sig figs? Look at your answer choice. 19.436, 19.4, 19.0, 19.43, 19.44. All of those are varying numbers of sig figs based off of one single answer. Guess what your calculator spits out? Answer C, 19.436. For those of us like Simon that don't want to enter anything in the calculator, you don't have to. That's what the calculator tells you. Now you have to deal with your sig figs. Okay? Yes, that's a trickier question if you wanted to ask about sig figs, but unfortunately we're out of time. Tanner? Yes, if you want your lab goggles, you can follow me to lab, and I'll pull them out so you can get them.